Welcome back, everybody, to the Virtual Residency Workshop 2021. It's Thursday, June 10th. This is the early afternoon session. We have a panel on low-cost solutions for research computing hardware and maximizing value from acquisitions. And our moderator is Chu-Ming Chen. So Chu-Ming, go ahead and get started with the panel.
Hey, thank you, Harry. Good afternoon. Welcome to the Virtual Residency Workshop 2021. This session is about low-cost solutions for research computing hardware and maximizing values from acquisition. My name is Chu-Ming Chen. I'm an associate professor of Department of Computer and Information Sciences at the University of Delaware. I work for the Center for Bioinformatics and Computational Biology and the Data Science Institute over there. My research includes bioinformatics, data integration, ontology, and high-performance computing. As you can see, we have a wonderful group of panelists for this session. So from them, you will hear stories of the low-cost research computing hardware, how to repurposing pre-owned hardware from other institutions with some specific examples. You can also hear lessons learned from a business school, as well as how to extend the life of high-performance computing system for collaboration. So each panelist will give a short presentation and will answer a couple of quick follow-up questions. At the end, we will have a panel discussion to address some of the broad questions related to this topic. So please type your questions or comments into the Zoom chat. And you can also type the question into a Google Doc. I will put the link to the chat shortly. So without further ado, let's get started. The first speaker is David Chaffin. David is the director of the high performance computing at the University of Arkansas, Fayetteville. David has 40 years of experience in computing and engineering, with the last 20 years in academic high-performance computing. He's going to talk about the repurposing of the X8 Tressler cluster. David, the floor is yours. Let's stop.
Okay, I tried to share a screen. Did you get a?
We're not currently seeing your screen.
All right, try one more time.
We are seeing about half of your screen.
Oh, okay. How's that?
Much better.
Okay. Title slide. As Chu-Ming said, I'm HPC director at the University of Arkansas, and this is the Trestles cluster, which is in the background of this photo. Looks more impressive in the dark. So we got this system from as a retired X8 or Teragrid system from San Diego Supercomputer Center. And this is the press release they put out at that time, back in 2015. So it had been there since 2011, and then about in 2015, we found out that the Comet cluster was coming to SDSC, and it was going to move Trestles out a little bit early for space and power. So my colleague Jeff called the then deputy director at SDSC. Turns out we were the first ones to call. We set up a meeting over there. I think they vetted us a little bit, and they eventually approved the transfer. So we needed about 70 thou for moving the system halfway across the country and upgrading our power and cooling a little bit to handle the new system, which was 10 racks. So that summer, we got it installed. There were about 260 nodes initially. And since then, we've been using it, and it's actually still in use, sort of. We had multiple years of more than 50 million core hours delivered by the system, which is all pretty good for the amount of money we have in it. The users still like it, and we're just letting it run as sort of an HTC resource that's usually immediate availability. And it's as soon as we need the space, I think it's going out the door because it's coming up on 10 years old. But the whole project was a pretty nice success. Everything aligned to make it work. We got some nice letters from NSF. One of our then assistant professors managed to get most of the calculations done that produced the paper that gave him tenure. So he wrote some nice letters to the chancellor about it. In equipment, since it's a cluster, basically you can let a node kick off, but there were some single points of failure. There's a Voltaire InfiniBand switch. We put that under warranty for a couple of years, and it's still going. Trestles was initially a bit, under designed for its racks, and if you put an intensive load on it, it would start kicking off PDUs. We just had to limit the load on each PDU a little bit. Eventually, the rack Ethernet switches all pretty much died, but unfortunately, we had a good stack of spares from our networking group. We mostly let the nodes die as they had problems. So we're now down from 260 to about 160. They're fully working, and it's mostly power supplies. I think they gave up. On the plus side, it's not overloading the PDUs now because there's not enough connected load. So we really didn't intend to keep it this long, but aside from the PDUs, it's been a pretty reliable machine. Unlike some that when they get old age, just start doing random failures. At this point, it's not really power efficient, and we're just kind of waiting until we need the space. I think some of the factors to consider if you're doing this kind of thing, calling first was a big help. Another big help is it wasn't completely worn out when we got it. And some other factors that we found pretty necessary were, a fairly experienced staff to take a cold machine with no support and install it, and a fair amount of space and power and cooling, and ability to get those facilities fired up fairly rapidly, and the funding to do that stuff. And that's the kind of thing that might not be available at every emerging center, but there are software solutions like OpenHPC and so on that can help you install a fairly large cluster even without much experience. So that's it.
I just kind of curious. Say that you mentioned lock to repurpose cluster. So how did you find out the chancellor is retiring or that type of thing? Do you have a particular connection? Or?
I didn't quite catch that. How did we find out what?
How did you find out the chancellor was retiring and?
Well, it was in the. We found out that Comet was coming and that Trestles was moving out because of that.
So you kind of you already had some kind of connection, or you know somebody.
Yeah, we knew a few people there. We heard rumors about impending Comet and decided to move on it fairly rapidly, and that was a help.
Okay. Also, I assume you. I mean, in order to host this cluster, you need a significant investment in your summer data center server room, or you already have such capacity, or you did invest in the server
Yeah, that's
yourself?
a good question. It was, it was 10 racks, so it's a fair amount of size and a fair amount of power. We needed about 30,000 in work on our cooling systems to handle it,
Mhm.
and about the same amount to move it halfway across the country. Of course, if it had been a little closer and a little bit lighter, it could have the moving would have been less.
Okay. Thank you. Thank you, Dave. Next speaker is Ben Overstreet. Ben has been at Georgia Southern University for past 4 years, where he first served in the role of custom relationship analyst for the College of Engineering and Computing. He entered the role of research system administrator in 2019, and in May become the assistant director for computing research support. Ben is going to talk about low-cost research computing hardware. Ben, the floor is yours.
Hey, thank you. More like free research hardware, but let me get my screen shared here real quick. Sorry, just a second. All right, can everybody see that?
Yes.
Okay, cool. All right, so yes, our research cluster is called it's called Talon, since we're Eagles. So back in around 2018, the previous director in this position acquired a approximately 220 stateless compute nodes. It was from the University of Arizona. It was in a SGI rack. Acquired their system. They were getting ready to surplus it, and he happened to meet the guys at a conference, and over a couple of beers got a free HPC system. So all we had to pay for was pretty much just the shipping and power hookup. So our previous cluster consisted of around 71 compute nodes and 1,600 computing cores. So we also, the new cluster is will be over around 300 compute nodes, with the 220 that have been added, along with a couple others that have been purchased over time, over the past year and a half or so. Most of our current hardware consists of surplus academic and enterprise servers. The academic side comes from our previous NetLab installment. About 13 to 15, depending on which ones work. Dell PowerEdge R610s, and the enterprise servers are mostly old blade chassis that have been retired. So this is the SGI racks that we acquired. Yes, so like I said, it's around 220 220 diskless compute nodes. They're 12 cores each, and some range between 24 and 48 gigs of RAM. So not super powerful, but they do have the 40 gig HDR InfiniBand backend, so that makes it a lot faster than a lot of the things we currently have. Most of our current setup is anywhere between 1 and 10 interconnects. So at the top of each rack, there's a rack leader, and the fourth rack included 3 service nodes, which we had repurposed as our storage nodes using the Scala file system in their software. So the SGI came installed with their proprietary software on a RHEL 5 operating system. We sort of had to reverse engineer it and figure out how everything was configured so that we could put our own spin on the system. We ended up having to use an IPMI tool to scan the internal network between the racks to get the IPs for the chassis management controllers, along with the IPMI MAC addresses. And we were able to export that information into a XCAT database, which we could then manage the IPMI from each rack leader and then use XCAT to provision the operating system to all of the stateless nodes. We ended up doing that. Our main cluster management system is ROC, so we chose XCAT because I don't believe, or at the time, I don't believe ROC supported stateless nodes. So our legacy operating system was 6.5, and we upgraded everything to 7.9, which I guess with end of life coming soon, we'll be busy at updating that again soon. The cluster management system was also upgraded from ROC 6 to version 7. And our Scala file system, so like I said, we used the old they were old super micro boxes, 3U boxes that we just stuffed a bunch of drives and new RAID controller in. Everything else was, I think they're about 10 to 12 years old. So we had a motherboard fail back in October, which then prompted us to eventually replaced the motherboard and then eventually replaced the chassis or the server itself with a newer Supermicro that was provided from Sans Digital, which is the parent company of Scala. The new storage will allow us to, it's got 16 bays rather than the 8 bays that we originally were provided with the old Supermicro. So right now we have 240 raw terabytes of storage. It houses our home, work, scratch, and the user local partitions or directories. So this part going forward, we're looking at sort of standardizing our purchasing requirements. Recently, the Office of Research has purchased us a new GPU node. Beforehand, the cluster was GPU-less. We had the College of IT recently purchased 2 R740s with one NVIDIA V100 in each. So that was basically our only GPU computing source on the cluster, and it was just limited to individuals within the College of IT. So the Office of Research recently purchased another one that was it's another R740 that's got it's got 3 RTX 6000s in it that will allow us to promote more, hopefully promote more AI research and just visualization type research on the cluster. So the new standard will be there's a 3-tier standard for basic computing, sort of mid-tier computing and advanced computing. And this will allow us for an ease of management as well as and maintenance. So I think that's all I've got. Yep. Kind of flew through that. So if anybody has any questions, just let me know.
Thanks, Dan. I just have a quick question. You mentioned your system is more like the heterogeneous node. So can you comment on how what kind of difficulty have you faced? I mean, in terms of managing this kind of heterogeneous system.
I'm sorry. Let me turn my volume up. What was that again, Jimmy?
You mentioned that your system is more of like the heterogeneous system. You have different kinds of nodes coming from different time. So have you had any sort of difficulty in managing all kinds of things? Some machines are old and retiring, and some machines are sort of they are in different architecture or that type of thing.
I think the most difficult issue was the SGI and getting it configured, because we couldn't find very good documentation on it, so we kind of had to fly blind a little bit as far as getting everything configured. We ended up finding the IPMI tool and was able to scan that internal network, and that helped push us along a lot further. But then getting XCAT configured, because neither me nor my previous director were very adept in using XCAT. Most of our experience was with ROC, so having to learn a new way of provisioning and setting up the net boot images, and so a lot of that was the mix of the two cluster managements was a little bit tricky to configure.
Here's a question from the chat. So a common argument for replacing old hardware is the power inefficiency. And the power efficiency of the new hardware pays off itself in power saving in 3 or 5 years. So can those who receive the retired hardware confirm or reject the claim? So do you have any comment on that, the power efficiency?
The power efficiency, so each of those racks are, I think they're rated at around, I don't want to get this wrong, about, I believe around 30 gigawatts each, or 30 megawatts each. So we ran into a lot of, we had to end up running new power to our PDUs in the data center, and so that was basically our biggest cost with adopting the SGI infrastructure. But we haven't run into any power issues since using it. That's unfortunately, it's right now our cluster doesn't get used a lot. So part of my new role is trying to promote the cluster and get more users on it to actually drive the power up. Because our data center is actually fairly barren, because it's a fairly new data center. It's only about 5 years old. So there's a lot of empty racks in there. So the SGI is actually helping the crack units perform to their potential. So sometimes when it gets low, I've written some scripts that submit jobs to the SGI cluster to just basically do a burn-in type thing and drive the power up, just so that crack unit is performing at its maximum or its optimum capacity. Okay,
thank you. Our next speaker is Christopher Simons. Dr. Christopher Simons is the Director of Cyber Infrastructure Research Support at the University of Texas at Dallas. He has over 20 years of experience in computational science and is also an adjunct faculty member in computer science and physics. He's the PI of a newly founded NSF CC STAR cyber team, Texas Research and Education Cyber Infrastructure Services. He's going to talk about the low-cost solution for research computing on the market value. And Chris, the floor is yours.
All right, thank you very much. Can you confirm you can see my screen and that my voice is coming in loud and clear?
Yes.
All right. Hey, everyone. As Chuming said, I'm Chris Simmons. I'm from UT Dallas, and I'm here to talk about sort of how we do guerrilla research computing, how we sustain research computing with the change in our couch cushions. So research computing at UT Dallas is relatively new. And about 4 years ago, we received our first donation from the Texas Advanced Computational Center. And that donation built our system known as Ganymede. And can someone mute? I hear some background noise, please. So Ganymede was established about 4 years ago, and I joined UT Dallas about 3 years ago. And we've made sort of a history or a legacy of taking retired systems and redeploying them with sort of lower barrier of entry requirements than a traditional HPC system. So all of our systems are based on OpenHPC. And as a disclaimer, I'm one of the developers and on the leadership team for the OpenHPC project. This is not meant as an endorsement, but OpenHPC is really cool. So we build all our systems on top of OpenHPC, and we've tried to put lower barrier of entry interfaces on our systems to enable equitable access to research computing resources. So, we have things like, remote graphical login nodes. We have, HTML-based web portals and file transfers. We support, Jupyter, RStudio, MATLAB, and begrudgingly ANSYS, as well as full Linux desktops. And, I joined UT Dallas about 3 years ago. And when I first joined, we had tens of users of our systems. But by sort of, repurposing more retired systems and building out our infrastructure and doing a lot of user help, we've managed to go from tens of users 3 years ago to 500 users on Ganymede, about 1,000 users total across all of our systems. So this has been very successful. In addition to Ganymede, we also maintain 2 other systems that have retired resources from TAC. We have Europa, which is going to be launching in the fall, which is actually a UT system resource. As was mentioned in the introduction, I was recently funded as PI of a CC Star cyber team for the University of Texas system, and we'll be redeploying retired systems from TAC and supporting UT system users who need a little more hand-holding to help get started running research computing workloads. And then we also run a system called BigTex, which is again from retired systems from TAC, which was set up in conjunction with the Dallas Federal Reserve, and we provide big text for all the Federal Reserve economists. And doing this over the last 3 years, we've run over 1.5 million jobs on this quote unquote free hardware. So what I want to talk about next is a new initiative we have going, which has some money involved, but it's meant to be sort of a self-sustaining data parallel condo system. So when I say condo, that's just short for condominium. That means the base infrastructure is provided, but PIs can come in and buy their own units. And I worked with the Office of Research to get a $50,000 investment a year for 3 years, so $150K overall. And I want to sort of show you what I'm going to spend this on and how I'm going to turn this into a sustainable system. So first, I think, for these smaller systems, we put too much emphasis on the interconnect, and getting a new like HDR fabric these days is extremely expensive, and it's a large fraction of your system. And if you're only running jobs on a few nodes or tens of nodes, you really don't need it. And working at AWS these last couple of years has sort of really hit home that not everything needs an InfiniBand fabric. And sort of doing some back of the napkin math, it's pretty easy to convince yourself that 25 gigabit is the price performance leader. For about 10% more expensive than 10 gigabit, you can get an entire 25 gigabit infrastructure. And we're building this on top of 2 25 gigabit connections per server. Now for the scratch storage, I really like BGFS. It's low barrier of entry. It's a pretty easy tool to use, and you can get a lot of functionality with the Libre gratis version. And the way we're doing this is with 4 servers. Each server is 4U with 36 drive bays. And it's really important that you look at how the drive bays are allocated in your servers. Those top loading servers give you a lot more density, but they're really hard to maintain. So I really like those 4U systems that are all front and back loading. So once the system's racked, you never have to remove it. Now with those, we couple that with either a hardware RAID card with battery back cache and then use XFS as our file system, or we get rid of all that and use ZFS. But ZFS and putting a proper cache with like an SSD in there requires a little more sysadmin experience. But XFS with a hardware backed cache is pretty easy. And another thing we do is we buy our storage servers partially populated. So we're only buying 12 disks per server initially, and we build it out horizontally first to scale performance. And then we add disks as needed to vertically expand a system to add to capacity. Now, for the actual server platforms, we've settled on the Supermicro SuperBlade platform, and they have these really neat 8U chassis that fit 20 servers with them. And in each of these sockets, we're just buying the chassis right now, and then we're going to buy a few blades here and there. One of the blades we're going to buy is an NVIDIA A100 with a 28-core AMD EPYC 3 CPU. And this 28 core is a really interesting piece of technology. Not only is it price per core much cheaper than any other AMD processor in that sort of performance range, The NVIDIA A100 supports something called MIG, multi-instant GPUs. And you can actually take a single A100 and divide it up into 7 logical GPUs. And then once you have 7 logical GPUs and 28 cores, you've essentially got a 4-core and 4-core MIG instance that you can then package and sell. Additionally, on this system, we're really excited about the NVIDIA A10, which just came out. And with the NVIDIA A10, a single A10 for about $10K per node, you can support 64 fully accelerated virtual desktops. And then within this model, PIs either buy a blade, or I'm going to buy a couple of blades and then slice off individual MIG instances and try to repackage those to lower the barrier of entry for PIs who want their own dedicated GPU resources. Then the other type of server we're buying on this system are what I refer to as JBOGs. These are these 4U systems that can fit 8 or 10 triple width GPUs in them. And JBOG is just a bunch of GPUs. Now, if you couple that with KVM, you can basically set up your own EC2-like service. And then what we do is we sell out individual GPUs and we slightly overcharge for each GPU to amortize the cost of the initial purchase. And once we fully occupy a JBOG, we then buy another one. And this is what sort of I refer to as stone soup computing. Especially, you put some initial money into it, my stone, right, which isn't too much, but then PIs come in and add the beef and they add the vegetables. And then if you then couple that with scavenger queues, which opportunistically give people access to any of these condo resources that are not used, or not being used, you really increase your utilization. And you also really create a nice resource for the community. So in order to finish this up, just some general recommendations of running sort of an HPC center on a shoestring budget. So as alluded to before, running a mixed architecture system can be challenging. I think on Ganymede, we have 8 or 9 different microarchitectures. And while the operating system provided packages are of course compiled at the x86-64 level, a lot of your user space tools that compile software, such as Conda or RDev tools, really do take advantage of microarchitectural optimizations from the compiler. And that makes it really hard, especially on our mixed architecture systems. Our newer nodes tend to be like our login nodes where they do the compiling. And then our compute nodes are older nodes, and you sometimes have problems with it. So what I really recommend you do is learn a tool like SPAC. SPAC is an amazing tool that can solve many of these problems and really makes it really easy to declaratively build architectural optimized binaries for every architecture on whatever login your node you're running, because it supports a rich feature of cross-compiling. Another thing is try not to spend your time managing users' Python and R stacks. Spend your time writing documentation on how to do it and teaching short courses on how to do it, but really make your users learn to manage their own user space package managers. Be wary of freemium services. A lot of things in the research computing space have the sort of drug deal model, right? Where the first hit is free, but if you're then successful and you now have 10 servers or 100 servers that needs the technology, it becomes quite expensive very quickly. So in general, I recommend investing in people and technology, not solutions, and focusing on Libra and gratis solutions if possible. A final couple of comments. Our single most popular resource that we've put into production has been graphical login nodes. We've just added a couple of more login nodes to Ganymede, and we installed X2Go on it. And if you're not familiar with X2Go, it's a Libra and gratis remote X client that connects over SSH that users install locally. And then you install the X2Go server on your graphical login nodes. And if we then install things like RStudio, PyCharm, all the IDEs people like, we've seen that to be an extremely popular resource. And finally, one of the things we're going to start doing with Europa is we're going to have a dedicated queue on our UT system called VDI. And VDI will allow users to run multiple jobs on the same node. Our typical policies are 1 job per node. But for the VDI queue, we're going to allow it to be oversubscribed. So each user will get 2 gigs of RAM of their own and a single core, but there's multiple users who can have simultaneous sessions on the same VDI node. And so with that, I will stop my talk and take questions.
Thank you, Chris. I have a quick question. So what's your storage archive solution for the system you just talked about?
Yeah, so that's a good question. So for Ganymede, when we made the initial purchase or the initial acquisition of the hardware 4 years ago, at that time, the university invested in a DDN GPFS-based spectrum scaler. So on Ganymede, we have a 1.4 petabyte GPFS parallel file system over the InfiniBand fabric. On our other systems, we've been building out MooseFS-based storage. So MooseFS is an open source, software-defined storage, which is very similar to Ceph, except the barrier of entry for MooseFS is much lower. So we've started with MooseFS for building out a couple of petabytes of backup storage, as well as archive storage. And then longer term, we plan to migrate to Ceph.
Okay. Thank you.
So, and I think we had a question. Oh, was not expecting to hear HPC financial arrangements compared to drug dealer. That is pretty close though, right? You know, the take-home lesson there is that these vendors with these very expensive solutions take the same model that drug dealers do, right? You see this all the time with premium software pricing. It's $10 per user per month for the first 5 users, and then it scales to be hundreds of dollars, right? And so I just try to stay away from any of those products, which exactly, it makes users a direct analogy. That's fantastic. And in general, I try to stay away from anything that allows me, as I said, victim of my own success. So we have another question. How do your user R managed package processes go? So there's a couple of different ways we can do it. So with OpenHPC, we do release R. So there is an R distribution you can install directly. And then from there, users can install their own packages in their home directory. But what I really try to get our users doing is to actually build their own version of R by going through SPAC. And so what I'll do is I'll work with users to figure out their package requirements, and I'll help generate a spac.yaml file, which will then allow them to take this spac.yaml file and move it to any system, and then declaratively and reproducibly recreate their user-defined software stack. So I really focus on sort of empowering the users to do it themselves, so they all get their own compiled from source version of R. So I do a lot of hand-holding initially and teach them to fish, but over long term, it is a much more scalable solution.
Okay, thanks, Chris. We'll move to the next. Hi, Chris. I think there's this question about X2Go and the Open On Demand. What's the difference between them?
Sure. I can take that real quick. So X2Go is just a virtual desktop, right? So it is a server it's a server process you install on your remote X server, and then people download a client for Linux, Mac, or Windows, and then they SSH in. It's like using VNC, except it's over SSH, and supports remote X and all that stuff. Open On Demand is a web-based client list portal for HPC. So Open On Demand is provided by the Ohio Supercomputing Center guys, and they do a really great job. And so with Open On Demand, you install stuff on a login node, and then you also install stuff into the compute node images if you're doing like stateless. And then with Open On Demand, you get an HTML5. That means no downloads, no plugins. It works on your laptop, desktop, mobile, iPads, whatever. You connect to the portal, you log in, and then from that, you can get a terminal. You can drag and drop files and transfer files through the web browser. You can get access to Jupyter and RStudio and MATLAB in just a web browser. So it's not a full Linux desktop, it's just the application. If you close the application and go to another machine or another network, you can resume that application in the web browser. And then it also supports a full desktop over VNC. So it uses no VNC locally in a web browser, and it works fairly well, but it requires much more setup than X2Go. X2Go is really, it's literally like an afternoon job to get it going.
Okay, thanks, Chris. Next, we're going to hear from Sean Strader. Sean is a deputy director of the San Diego Supercomputer Center at the University of California. He is specialized in the development, acquisition, and the deployment of HPC systems. He is the co-PI and the project manager of San Diego Supercomputer Center's commit system and expense system. Sean holds a BS in aerospace engineering and a master in aeronautics and astronautics from Stanford University. He's going to talk about how to repurposing several of the HPC systems. Sean, floor is yours.
Howdy, you see my screen okay?
Yes.
We good. Okay. Well, thanks so much. So yeah, I'm the deputy director at SDSC and wind up in a project management role for a lot of our HPC systems. And I suppose my unique perspective would be around these larger scale systems and and some of the procurement related kinds of things that might be a factor in when you decide whether or not something like taking on another system is in your best interest. The first one's free kind of analogy that folks have raised. So I'll just do a few examples and lessons learned here that I sort of thought about as we were thinking here today. Already we've talked about the trestle system. I don't need to go into a bunch of details on that. The timeline is at the bottom here. It started out somewhere around 2011 in terms of acquisition and all that. And at this point, from what I can tell, it's kind of sunsetting. It's served a long and useful life. And there was some serendipity to relationships, I think, that folks pointed out, which is, I think, probably a pretty big takeaway for this group. I heard somebody said something about beer being involved in one of these deals. So who made a call? Who was at sitting at Perk over a coffee one morning, and maybe somebody mentioned something. And so these kind of deals happen that way. It's really about the networks that you're in and the folks that you're interacting with, where you learn about these kind of opportunities and whether they make sense or not. This was a MagnaCore system, a 4-socket MagnaCore system back in the day, which did fairly well for us. I heard a mention of shared node computing jobs. That's been a practice of ours now going back, I think, as far as trestles. It's a highly effective way to get the most out of your system. And so, also I heard a comment about interconnect costs. That's absolutely another very smart thing to do. You can spend 30% of your system acquisition on networking if you're not careful. And so our systems, other than trestles, which was a small compact system with a single director class switch, all of our systems subsequently have had some form of an oversubscribed or different kind of interconnect fabric in terms of being cost effective for our mix of workloads. In fact, the system that came on board really right around the same time as trestles was our Gordon system. That was a 3D torus system. It had 2 mirrored torus networks on it, one for storage traffic and one for compute. Again, a very effective interconnect because it was oversubscribed between nodes on the torus, but you had a fully connected set of compute nodes that sat on each of those switches. So this was a 1064 node Sandy Bridge system. It had a long and useful life at SDSC starting in 2012. We actually cleared this system out recently to make room for our Expanse system, which is another NSF system. This particular system was, we entered into an agreement with the Flatiron Institute, which is an institute funded by the Simons Foundation that has a portfolio of doing neuroscience research, cosmology research, biological sciences. And again, this came out of relationships that we had. UCSD involved in the Simons Observatory, and we have folks that are doing research with them. And again, you know, became aware of the system ending its life. And so before that, the Simons folks, the Flatiron folks, essentially got time on the system. And some of these systems allow the centers to make some amount of it available via some kind of a recharge or a director's discretionary allocation. So Simon started using the Gordon system as a partner. You might think of it as an industry partner, but in this case, it was a not-for-profit research institution. And so that system, once we decommissioned it, they ran it for a while, and that's since been taken out and is now being sort of taken apart and parted out, if you will. We've retained a few nodes for development and testing. Some of the research staff have a handful of them. So these do have a pretty long useful life. This system had a lot of flash memory in it. I had Intel's first data center SSDs, and we've looked at the wear statistics on these things, and they were incredibly reliable. And still, if you look at the smart stats on these, they to this day have a lot of life left on them. You know, you think you're going to do a lot on these, and then when you sort of average that out over the scheduler and multiple users and so forth, you know, that pretty much levels out the use of the flash. And so this has been a real success story. We had flash and Trestles as a sort of Trestles was deployed after Gordon was awarded. So we were already sort of all in on the flash game. And so Gordon became, you know, our big flagship flash-based system that we ran, and that continues, and I think has become fairly, you know, obviously flash memory is everywhere in HPC and elsewhere. It's the right thing to do for many workloads. So again, you know, main message here is this came out of a collaboration. This did not go off-site. It simply sat there, and then we decommissioned it in situ there. So today we are winding down our Comet resource, which was the successor to Gordon, it is a roughly a couple thousand node Haswell-based system that has also some GPUs in it. It's largely standard compute. Like Gordon, like Trestles, these are systems intended for a very broad user base. By virtue of sort of that broad user base, you know, that's how we come into contact with a lot of collaborators as well. I'm sure the Arkansas folks were allocated users on Trestles at some point, I'm guessing, and there was, you know, there's a lot of connections that one gets in the community, and I'm sure even at a campus level, you know, you've got all these different PIs that are coming in, and you know, I've heard I think Chris talking about what is this essentially a condo system he's putting together. You've got a lot of different PIs, mixed workload. Those are all the sort of roots of collaboration, and I think you know, how you connect with your PIs and your researchers. Not just supporting them, but understanding the science they're doing, where they're headed and whatnot is really important. And in this case, with the COMET system, the Center for Western Weather and Water Extremes, CW3E, had also been a user of the COMET system. And as they became aware that it was going to be decommissioned, they expressed an interest in taking it over. Now, this again is a local collaborator. It's at the Scripps Institute of Oceanography. And obviously we've had long collaborations with them. And so as we wind down COMET, it'll sort of formally end NSF life at the end of July. We're moving folks off of that now. It will be repurposed into a second life as a resource for this team. This is, you know, atmospheric modeling, ocean modeling. This is a computationally very expensive kind of field here. And so they'll be taking essentially about 80% of the system. You know, some of it will be there for cannibalization for parts and so forth, as you all know. I did want to go back real quick and just mention one thing that I didn't say here on the Gordon system and Flatiron. They have since deployed a whole HPC cluster now at SDSC. So they've deployed in this case several racks of a Lenovo system, multiple generations of hardware, most recently some racks that are liquid cooled. So this deal, if you will, with Gordon has led to, you know, ongoing collaborations with the Simons Foundation, and they are now hosting some systems in our data center that we provide some system support for. And we've learned a lot from them too. They've deployed a large Ceph file system on their recent purchase, and we're learning a lot about Ceph and how it performs in different workloads. We've had a seminar from one of their team about their experiences with Ceph. They were actually the first sort of commodity cluster to be liquid cooled in our data center. So that actually spurred us to get more of our infrastructure in place for our Expanse system, which is also liquid cooled. So, you know, you can just see there's multiple connections here that sort of emerge out of these collaborations, and they go in all sorts of different directions. But again, I would just say that there is collaboration at the root of this. We're not in business to make money off of these deals, really, but we have a strong interest in collaborating. I guess I'll wrap it up with some lessons learned here. There were some comments about power and so forth in the chat, you know, and I guess, you know, to some extent, these different kinds of Second Life are market driven. People are expressing an interest in these systems based on their own unique circumstance. However, power's covered, whether or not, you know, they may not have the funding right now to go buy another HPC system or a large cluster. So, you know, I guess you get the system you can, and not necessarily always exactly the system you want. The cost of doing procurements and standing these up is substantial. And so there's a whole nother bit of efficiency here when you can take another system and give it useful life. And what's useful life here? You know, we're talking about maybe a couple extra years of life. And at some point, as folks have pointed out, you know, the performance to power ratio just becomes unattractive. Yeah, you know, and you just can't justify it any longer. You know, the bathtub curve, as they say, of parts failure, you start to see stuff failing faster than you can find replacements. You may not be able to get replacements at all. Of course, you know, there's different ways to mitigate that that I think some of you have talked about a little bit. But so, you know, of course, there's a new dynamic right now. I think about GPUs. I'm trying to buy one for a new gaming system I'm trying to build, and I literally cannot get them, of course, because they're virtually impossible right now. Be a little easier to get some of the A100s and the stuff that I think Chris pointed out about MIG. Very interesting that you brought that up. That's something that we're very interested in looking at ourselves. So, but point is, you know, there's opportunistic elements to bringing these systems in that make sense for the different folks you might be working with. It made sense for the Arkansas folks. It made sense for the Simons Foundation, and it made sense for SIO. And those will be gracefully degraded and put out to pasture, you know, when their times come. The hardware can last a long time. You got to think about that from the beginning. When you know you're going to be reaching out a little longer, buy up every part you can. You think you might need, you know, power supplies and whatnot. You know, odd things can become difficult to find. At some point, you know, you just can't get a Mellanox QDR switch anymore. Okay, you're kind of done there, and there's nowhere to find them anymore, and so you're just out of luck. You know, a lot of these applications don't have the vector performance. And so even though you get these successive generations of processors, they don't give you a whole lot of performance improvement necessarily. So that's a factor. They do generate, these deals a couple times have generated some sort of flexible revenue, not a lot. Maybe let you do a little synergistic work, you know, maybe the Simons deal spins up a little funding and we can go get our own small, you know, test unit and work with them on some sort of a, you know, a Ceph project or something. So it's helpful. I think if you're going to enter into any kind of agreement on these sorts of systems or deals where you're delivering services, you really need to set expectations up front. I mean, our service agreements are structured with the full foresight of knowing that, you know, there are hardware potential issues that will come up. You know, what's the scope of services you're delivering? You know, this is like anything you would do, I'm sure, in your different organizations, to make sure that you're not, you know, you have this open-ended deal that can get into trouble, then pretty soon everyone's calling, you know, all your team. So we do structure those very, very rigorously to make sure that we're doing what we can. I think that's all I had. Again, we're still learning about all this, and it's fun. As long as you keep in mind that you want to have a collaboration, you're not really just in business to run systems. I hope you want to do the science and support the researchers and so forth. And that's really the driving force for us when we enter into these deals, and hope that we're helping other folks as well do the same thing. So thank you very much. That's all I had for slides right there. Happy to take any questions or comments, or open it up for the panel after the last speaker.
Thank you, thank you, Sean. And thank you for sharing your lessons. And I think we're going to have a lot of to discuss in the panel. So I'm going to move on to the last but not least speaker, Jason Wells. Jason works at the Bentley University as a senior research computing consultant. He was a programmer, IT project manager, senior member of IT, and a mentor until a research asked if his startup program could be sped up. Jason is also a Exit Campus champion, member of the CCC and the EduCourse Research Computing and Data Community. Jason holds an undergraduate degree in Computer Information Systems from Bentley University and a graduate degree from Norwich University. He's going to talk about the low-cost computing from a business school perspective. Jason, you can start.
All right. Hopefully, we've got the slides up. I want to thank
Yes.
everyone. I want to thank everyone for giving me a chance to talk about this. At Bentley's a small business school near Boston, and literally, I'm the only person on campus doing supercomputing. So I've done everything from the budget up through the, helping people with their code and whatnot. So consequently, I'm known as that supercomputer guy. Let's try and minimize this. Never works. Our first commit cluster was actually just a decommissioned virtual server hardware. And I found out about it in a change management meeting. They were talking about implementing some new stuff. And I asked, well, what are you doing with the old stuff? And they said, oh, we're going to throw it into recycling. And I said, fine, please don't do that. I'd like to have it. And but at that point, I'd been at Bentley long enough where they said, okay, before asking, what are you going to do with it? And I finally fessed up to wanting to build a supercomputer. And that's how supercomputing got started at Bentley, was just this one little meeting. There were some upgrades that happened. We took the networking up to 10 gig rather than 1 gig, and I upgraded some of the drives so we had a bit more storage. But that served us very well for about 3 years, and then security concerns came in and actually tanked the system. They were afraid that people could get into the chassis controller and then bridge between the blades and finally access the Bentley network. So it was a very easy start, but you really have to make the most of it when you're doing this. Look for other people have covered this as well, but I wanted to kind of provide a canonical list of everything. So like you're in CARC, that's fantastic. There's the campus champions that you can be a member of, or you're an ACI rep rather. CARC is out there. There's regional efforts like in New England, NARIN, and UMass HPC days. There's vendor efforts like Dell has their own HPC effort and consortium that you can get involved in. We've got corporate and foundation relations at Bentley, and I'm sure you all do. Talking with them is fantastic because they have a lot of grant and donor opportunities that you can really get into. And then there's internal grants as well that you can make use of and that your faculty can make use of. And so it's really a matter of getting all those people talking about what you're doing. In particular, it's good for them to know what's happening because they'll start planning around your needs. Talking with the faculty, Bentley actually got a 42 node cluster. The security folks, again, wouldn't let us use it, but we got it. But that was through a faculty connection, that there was a business that was closing, and we're in a biotech hub. And so we just got all these servers from this one company. And then eventually able to donate them on to some folks that weren't quite as security conscious as us. Cold calling big centers. You just heard plenty of stories about cold calls that were successful. And then you really need to start networking with all of these folks. One way that I do the networking is these presentations. It's just a matter of getting your nose out there and finding out what people are doing. And oftentimes there's email lists that are happening where people are talking about free hardware that's out there, or grants and donations that you can be involved in. And then finally, if that doesn't work, consider a condo model. You've heard people refer to this today. The idea is that your researchers would pay for compute and or storage on your cluster, and that's can be a really useful model. I hear a lot of places that do that and then eventually move to a centrally funded model because they dislike it, but it's another option that's out there. Sizing a new system, if all that fails, it really matters what your researchers are doing. Bentley, I've got people who are chucking around 20 to 30 gigabyte files. And so the networking becomes a really important thing. I may only have a couple hundred cores for them to run on, but having fast access results in the worst comment I've ever had, which was, I think my laptop is faster prior to doing this. And that's the biggest insult that someone can say to one of us right now. But the data sets are what are going to tell you the networking speeds that you want, and then the algorithms that they're running. For instance, if they're doing MPI, we really need to think about getting low latency type of stuff like InfiniBand. Otherwise, I would do a 100 gigabit Ethernet. Storage, the sizes of those data sets really matter, and so people are processing these data sets and then exporting them, and so 20% probably on top of the size of your data sets is going to tell you how much storage to get. And then for the compute, I've got one researcher who's using 90% of all of our resources, and I literally have to call and beg him to cancel jobs or stop jobs just so that I can let other people use the system. That's pretty common, and the idea here is just that we want to have as much compute as we can and have it be very homogeneous. That way that it's more easy to maintain and use and have other people use. Okay, business school talk here. CPQ stands for Configure Price Quote. I don't know how many people at smaller institutions know this, but it's an industry that Gartner has valued at billions of dollars back in 2018. It basically, the whole idea when you're talking to vendors is they really just want to configure a complex system for you, give you a price, and generate a quote. And it's set up for quantity. They want to do hundreds of these things, and so you really shouldn't feel bad about getting and talking to numerous vendors, as many as you can and want to find out what they're offering and what they're willing to give it to you for. And being a business school, we play the vendors off of each other. I know it's kind of rude, but I'll say like, well, hey, Dell's willing to do this to HP, and they'll come back with a better quote that's a little bit better. SC's vendor space is a fantastic place to go to collect vendor names if you don't have names right now. I just mentioned two, but there's hundreds of vendors out there that are worth talking with. And then just as a final point, I wanted to say, don't forget about sustainability there. Just it's something we always have to worry about. Whenever you're purchasing new hardware, there is a way even now to save money. You can consider the length of term on the service contracts, or whether or not you even need one, the type of bezels that you're buying, the type of rails, and then whether or not you need cable management arms. A lot of times the power supplies are redundant, and so do you need that redundancy or not? And then the bundling of network gear is also an issue. You can shop around, or you can buy it from the vendor that you're getting the servers from. There's just a number of different things that you can do. And so it's worth thinking about that whenever you're going through with it. Some of these are going to give you more headaches, obviously, but if you can put up with the headaches, it's worth it. And that's all I pretty much had to say. I did want to talk a little bit about this server that you see in the background. That's a overclocked gaming computer that I put together, and has actually been one of the most useful things that I did at Bentley, actually, was to start running faculty code. We have a lot of CAN software, and so we've got people running SAS and SPSS and things of that nature on this, and it gives them a taste of supercomputing power. And that's been kind of one of the biggest marketing gimmicks that I've had, was just to let them run on that thing, and they get addicted to it, and all of a sudden I've got people who want to use the supercomputers. So please feel free to email any questions to me. It's jwells@bentley.edu. Thank you.
Thank you, Jason. Here's a question from the chat. How do you play the vendors off of each other without running the flow of the state bidding rules?
How do you play the vendors off of each other without running? Private institution. Don't have to worry about that.
Okay. No,
That's an extremely good point. Don't do that if you're a state-run institution.
I have a question. Say that what's your relationship with your university IT, or do you get help from them?
University IT.
Yeah.
I'm in academic technology, which is part of IT,
Oh,
but
okay.
not tightly so. The guys back in like the systems department are constantly trying to get me to move over there. And so I work with them very, very closely. It's been nice because they're kind of the only folks at the university who understand what I'm doing. I can talk about cores with them, but the rest of the institution doesn't really understand it. But you know, it's tight.
Okay. Okay, then let's move on to the panel discussion. I'm going to share my screen, and so we can have the questions. Okay. Can you see my screen?
Yes, we
Yes.
can see your screen.
Yes.
Okay.
Oh, now we can't.
You should say the first question.
Chuming, we
Okay.
could see it, but now we cannot. You did something.
Oh, really? I don't know.
Perfect.
Okay. So I think for a lot of people, how to increase the utilization of their resources is always a priority. So can you talk about your experience of increase your utilization and resources, and which one you should go first in terms of increase the utilization?
I kind of touched on it in my last one with that little server, the gaming PC. I had a lot of folks who were using laptops, and the complaint was whether or not things were faster on my stuff than their laptops. And so giving them the access to that system really opened a lot of eyes.
So, you know, in terms of my experience with trying to increase utilization of resources. So, you know, at UT Dallas, we have focused a lot on sort of lowering the barrier of entry to research computing and sort of equitable access, both in terms of institutions as well as in disciplines. And when most people go from their laptop, desktop to an HPC system, the first thing they do is take whatever workload they're running on their laptop or desktop and run it 1,000 or 10,000 times, right? It's really hard to think about what next big problem can I solve, but it's really easy to go from laptop, desktop to parameter sensitivities, to error estimations, to uncertainty quantification, to running the same job 1,000 times and twiddling a single parameter. And most of these users who do that use tools like Python or R or Julia or MATLAB. And you know, at UT Dallas, we've talked before how we sort of have a one job per node sort of policy. So our early education for these new users really focuses on high throughput computing tools. So stuff like TAC Launcher, which if you've never used is an amazing tool, which allows you to batch up hundreds or thousands of jobs and has a very simple way to interface with Launcher and then submit a single job. And then it'll automatically build a work queue. And then as a core frees up, it'll load it with the next one. And just giving them those tools, which sort of help them translate from laptop to thousands of laptops, is really what is done best to increase our utilization.
So from our experience, I think that for a lot of users I think the same missing here is the training, sort of how to let people know about your HPC cluster, how to sort of really have a good use of it. It's also very important. I don't know if you have the same sort of experience or
Yes, education is always extremely important, right? Especially when you go to new users. And you know, we do short courses and documentation and things like that. But one thing that was actually really successful is this spring, I taught a graduate class, which was out of the second year graduate class in physics, also available to any natural science student called Practical Research Computing. And while 20 students enrolled, since I did it all online and recorded all the lectures, about 50 people attended and about 100 people watched the lectures per week. So, whenever you do training, especially in this new, post-COVID world, make use of the recording technology and repurpose your lectures over and over again.
If I can move to the second question. I think that this is the sort of the same of these sessions. How do you deal with the old hardware? I think in the chapter, there's a question of when you're trying to use this kind of old system, whether you set up a date or how do you decide to really stop using them? And also, there's an issue of how do you find the spare part for this old system? And because since the technology is moving on, so sometimes it's very hard to get a replacement. So any of the panelists?
A lot of our hardware here at Southern is, like I said, with the academic hardware is a lot of the same Dell R610. So when those die, we just kind of gut them and save a lot of the resources that are still good. And whenever the time comes, we'll repurpose that and put it in other systems.
Yeah, I mean, I think several of the folks talked about their challenges in finding hardware replacement. You do have to be aware of that. You do everything you can to locate spares in advance, knowing generally you know what's going to fail. You know the common parts. They typically be, a lot of them are the ones that have moving parts. And then that question about space and power, that's absolutely a consideration. I think David kind of talked about that a little bit, but just generally, the larger systems, they can take a lot of room when you look at the footprint of how much computing per square foot and, performance per square foot. And that becomes a determinant. I think somebody put in the chat here about, their criteria for when it's time to push it out the door, about the time you ask that question usually. So that's just my 2 cents on
it. Anyone? Oh, okay, let's move to the next question.
Well, I will say, as sort of was alluded to earlier, if you're working with an old system with a high performance interconnect, the main thing that you need to worry about is InfiniBand cards, because HDR is not backwards compatible with EDR, QDR, FDR. So go to eBay and stock up on a bunch of QDR and FDR InfiniBand cards if you'll need them. RAM and other stuff and hard drives you can find, but InfiniBand, the older one, is going to be hard to find.
Okay, let's talk about those questions. So how do you actually make a good use of investment? And also, what are some of the benefits by extending the lifetime of your system? Anyone want to make a comment?
Well, I can talk about that a little. Well, we think Trestles was a pretty good investment because we have maybe 100,000 total cash in it plus electricity, and we run almost 2 million jobs, I think, since it's been here. And then the benefits to the institution are I think are obvious, to free up funding for something else until the point where the electricity is worth more than electricity is costing more than it's worth.
So from your experience, do you just basically, okay, for example, if the vendor gave you something like a 4 years warranty, so you just use your system in 4 years. After that, or even before that, you consider replacement or retiring them, or you You want to expand the lifetime of the system.
Yeah, I think Trestles was out of warranty when we got it, so it wasn't really a consideration, except we extended the warranty on the one irreplaceable part, the InfiniBand switch. But I think, as I mentioned in the talk, if the nodes died irreparably, we didn't really spend any money on them. Parts were pretty available, especially on eBay. But with what they cost, it's not really cost effective to start fixing those things after they have some years on them. So we just let them go.
Okay.
The vendors of some of these, you know, we did an extension on Comet that was still under NSF funding. You know, we did to run it an extra year. And the vendors get a little bit squishy when you start asking them for warranties too far out in the future. I mean, we were fortunate we got one more year out of them, but that's not going to happen after a while. They literally can't make them. They're not making them. You can't get the parts. They're not going to warranty anything. And so I think that what everyone's saying here is, you know, it's up to the entrepreneurship and of the individual to go off and find what you can find, and then put them in a big box somewhere and hang on to them.
Okay, so we are about to actually we're out of time. So let's discuss this last question. I think this question probably a lot of people are interested in. So is any regional group that can donate this hardware, and what's the best approach practice to approach the company, ask for donation or anyone?
You know, in general, when you're approaching a company, you know, it's best to come with something to the table, right? Just don't say, just give me hardware, please, right? You know, try to either get buy-in from the university, you know, get a, you know, a cost share contribution equivalent from the university to buy hardware to go with the donation. Or what I do a lot is I write, you know, papers and I write proposals that use hardware. So I say, if you're able to give us some certain type of, you know, resource, then I will commit to writing X number of proposals or, you know, featuring the purchase of your hardware. You know, you try to do like an in-kind kind of contribution.
Yeah, I think companies also have the way they allocate their funding, you know, some of it could sit in marketing and other units. And so making sure you understand the different roles within a company, that you could get a no from a sales team, but you might get a yes from a marketing team, you know, about it. Also, you know, where universities, things that are focused on students is really good too. And we've had some success around student angles and from companies and whatnot. And I think, you know, I don't hear any shyness in the folks on the panel here. You know, you just ask, they can tell you no. And again, you know, I think of one of the slides mentioned the multiple regional networking groups. You know, I think it's just, this is a terrific group of people here with a terrific network, and there's just there's no lack of ways to mine your network for some of this kind of stuff.
Okay, we are run out of time. So I would like to thank Henry for organizing this workshop. And I also like to thank the panelists, David, Dan, Chris, Sean, and Jason, for their insights and discussion regarding this fascinating topic. And also I want to thank the audience for their questions and comments in the chat box. Thank you. Get back to you, Henry.
Thank you, Chuming, and thank you everyone for a terrific panel. We learned a great deal from it. I'm very excited by this. Let me shut down the recording.